Okay, this is part 3 of rational functions. So what we did is we moved the x from the numerator to the denominator. So again, we're going to answer the 4 questions. First is the y-intercept. So to get the y-intercept, we set x equals 0, and you can see what's going to happen is these 4 terms will be non-zero, but this term will be 0. So the answer is going to be y equals 0. So f of 0 is 0. The second one are the x-intercepts. So what we do is we take the factored form of the numerator, so n of x, and then we set that equal to 0. And so there are now 3 intercepts. There's going to be one at x equals 0, one at x equals 1, one at x equals 2. The vertical asymptotes, that's where we set the factored form of the denominator equal to 0. So in this case, we only have 2 vertical asymptotes, and those occur when this equals 0. So that happens when x equals 3 and x equals -3. So those are the 2 vertical asymptotes. And then the horizontal asymptote. In this case, because the order of the numerator is going to be 3 and the order of the denominator is going to be 2, the horizontal asymptote, we don't have one. So there is none, but we do have a slant asymptote. And we haven't talked about that yet, I don't think. So what you do with slant asymptotes is you take the original function in its multiplied out form. So what we'll have is x times x squared minus 1 divided by x squared minus 9, and multiplying x times these 2 terms. I got those from multiplying these 2 factors together. You get x cubed minus x over x squared minus 9. So you use long division to simplify this or rewrite it. And what I'm doing is I'm adding the 2 terms that are not explicitly shown there. And then we've got x squared plus 0x minus 9. So to do this, we say, what do we need to multiply x squared by to get x cubed? Well, the answer is x. So we choose to put that up here. X times x squared is x cubed. X times 0x is 0x squared. X times -9 is -9x. We're going to subtract that whole thing from this. These cancel out. These are both 0. Here we have -9 times negative times -9, so it's +9. +9 minus 1 is going to be +8x. Okay. And that's our remainder, because we don't have any number that we can multiply x squared by to get x. So if we can rewrite the original expression as, so this can become x plus 8x over x squared minus 9. So this remainder, 8x plus 0, is the numerator, and this is the denominator. So this is our slant part of the whole thing. So our slant asymptote is y equals x. Okay, so now we're going to, and I'm going to skip the intermediate points, I think. I'm just going to show you how this would work. And here you can see what it's going to look like. But let's see how we get to that point. So we had, let's see what we got here. X and y intercepts. We got a y-intercept and x-intercept 0, and this was wrong. This should be -1. Okay, so we got 3 x-intercepts. One at 0, one at +1, one at -1. We've got 2 vertical asymptotes. One at -3, one at +3. And then we got the slant asymptote, which is going to run through here up there. So that's y equals x. So what I'm going to do is I'm going to take this and just move it to there. So it's outside of the largest vertical asymptote. So I'm going to do the same thing down here. So it goes all the way over there. But then I'm going to pull that here. And again, if x is large, it's going to be positive. It's going to be a positive value. So we know that this, and we also know that this is going to increase to infinity as x gets large. So what you have is you have something that kind of looks like this, and the same thing happens down here. And again, because we have single roots at x equals -3 and +3, we know that it's going to flip from negative infinity, positive infinity. It's going to come down here. It's going to go through there, like that. And we have a problem. So that's not going to work. Why isn't that going to work? Because this goes to positive infinity, so it has to come down here. So the only way for that to happen is this thing to loop down like that, up through there, down through there, and then all the way down like that. Now, if we had calculus, we'd be able to figure that out more so. But that's the only way you can get this thing to happen. And really, if it came down here, it can't go straight through there because you missed that 0. So it has this little loopy-doop there. And, if I wanted to find this thing more details, I'd probably pick x equals -4 to find a point here, and x +4, one here, and then I'd pick points between here and here and here and here to try to get some idea of how this thing loops around. And you can see that happening. Now, one thing you'll notice is that I way overestimated how much this thing looped up and down. You can see that there's it doesn't hardly get above the x-axis. You can also see that the scale that they set up automatically is much bigger than mine to try to capture everything. That's another reason why this looks smaller, is because I used a scale from 0 to 10 here, and here they use 0 to 25. But you can see that I've gotten the general idea of the shape of this thing. Okay, and here are the rules for horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. If the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is equal to the ratio of the coefficients in front of the highest order terms. And if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. There's usually a slant asymptote of some sort. Okay, so that's the end of my kind of working through all these different scenarios. They're all the same. You follow these rules. Find by setting x equal to 0, find the y-intercept. Set the function equal to 0, find the values in the numerator that make the numerator equal 0. That's by factoring it. Same thing in the denominator to find the vertical asymptotes. You can find the horizontal asymptotes using the rules that we just went over. And if you want to have a better, more accurate curve, you want to plot at least one point between and one point beyond each x-intercept and vertical asymptote. And that's, which points you choose. You can, by kind of sketching it based on the first four, you can have some idea of where it might be best to choose the x values to better define the curve. So here are a couple of extra problems that are like in the book. They're probably not going to do as ones as complicated as the ones that I've done. So, but I'm going to work through them anyway. So what we have here is we have the numerator is just a constant. So we know we're not going to have any x-intercepts because there are no values of x where the numerator goes to 0. But that's not usually. The first step is to find the y-intercept. You do that by setting x equal to 0. So f of 0, in this case is 4, divided by 0 minus 2 cubed. So that's 4 divided by negative 2 cubed, which is negative 8. And you can simplify that down to negative 1/2. So that's my y-intercept. The x-intercept, so just said there are none because there are no values of x where the numerator equals 0. Number 3 is to find the vertical asymptotes. In this case, there's only one. So that's when x minus 3 cubed equals 0, and that happens when x equals 2. Now, what does the cubed do in this case compared to just, say, 4 over x minus 2? Well, it turns out all it does is it makes the approach to the x-axis more quickly compared to, but the general shape is going to be the same. And then you got the horizontal asymptote. And there you use the rules. And because the order of the numerator is 0, you have x to the 0 power, which is 1, is less than the order of the denominator, which is 3, that means it's y equals 0. It's a horizontal line. So now let's draw this thing. And then we might pick a few points just to clean it up a little bit once we have the general idea. And because the vertical asymptotes are 2, I'm going to use 2 ticks to represent 1 unit. So this would be 1, 2, 3, 4, 5. And yeah, I think I'll just still stick with 1 unit per 2 ticks here. Okay, so we're going to have a vertical asymptote x equals 2. We have a horizontal asymptote of 0. That's not what I wanted to do. Okay, let's try this again. Horizontal asymptote 0. And since there's only one horizontal one vertical asymptote, I'm going to draw this horizontal asymptote both ways. Okay. and we had a y-intercept at -0.5. So that would be right here. So we know this has to stay here, and therefore this we have no x-intercept, so there's no way this thing can loop up. And we know that as we go to -infinity, this thing's going to approach 0, so it's going to come down something like this, and then it's going to go down here, and then because we have an odd number of roots, it follows the kind of the opposite approach. So it looks like picking a point here at x equals 3 and say x equals 1.5. So we're going to evaluate the function at 3 and at 1/2, and then we'll plot those. And the function was that. So we're going to have 4 divided by x minus 2, but x is 3. So we'll have 3 minus 2 cubed. So you get 4. This is 3 minus 2 is 1, so this is 4. And if we do the same thing with a half, 4 over 1/2 minus 2, or was it 1.5? I think it was 1.5, really. Is that right? Yeah, 1.5, not 1/2. Okay, so this is 1.5. So I got 1.5 minus 2 cubed. So that's 4. 1.5 minus a half is -1/2. -1/2 cubed is -1/8. And there you get -32. So I probably shouldn't have chosen that because that really goes fast. Probably f of 1 would have worked out better. So you'd have 4 divided by 1 minus 2 cubed. That's -4. Okay. So what I'm going to do is I'm going to erase these lines. So f of 3 is 4, and the x-intercept was, or the y-intercept was -1/2. So that was here, and f of 1 is -4. Okay, so we're going to come along through here, through then. This thing dives off pretty rapidly, like that. And up here we have the other behavior, like that. Yeah, I'm trying to decide how fast this thing, I think this thing comes down pretty fast, really, like that. Because there should be some kind of symmetry to this whole thing. I'm guessing because this is 2 units to the left of the vertical asymptote, and this was a half. I bet this, if you went 2 units to there, you'd probably get a half as well. Okay. And let's see what else we got here. Just looking. Okay, so we got quite a few more pieces here. So I'm going to stop for right now, and we'll continue on